This video on optimization is really all about word problems. I know, word problems can sometimes be very hard. Here I propose a little strategy which can help us to understand and to solve an optimization problem. The strategy consists of 5 points. First is to understand the problem. Of course, it's very important to understand the problem. Read it carefully. In particular, you should identify what is unknown, so what are you looking for, and what is given, so which information can be used. Then it is often very helpful to draw a diagram. Quite often we do something like a little flow diagram, so we say U transforms into V or something, etc., etc. So that's what I mean by a diagram, because a diagram can kind of clarify your thoughts and clarify the logical flow of the arguments. Then we introduce notations, so all variables need names. Then it's good to use intuition for the names, so we often use T for time, A for area, etc., etc. And then Q is mostly used for the quantity that needs to be maximized or minimized. And then we need to do math, so we want to find a formula for Q, and then this involves the other parameters and variables, and then we simplify this formula as much as we can. In the ideal case, we come down to one variable, so that we get a function q of x, and that's it. And then we can use our maxima and minima methods, for example, the closed interval method, looking for critical points, looking for minima and maxima on the boundary, etc., etc. So then we optimize q by finding maxima or minima values, whatever is needed at the moment. To help us memorize these 5 steps, I wrote them down here again. Understand the problem, find the known and unknown, draw a diagram, name all the variables, find a formula for Q, which is the quantity to be maximized or minimized, and then do maximization and minimization. So I highlight certain letters in all these items, and then if I put them together, I get a mnemonic U draw names for max and min. So I do now 2 simple examples in this video, and we let us lead by the saying U draw names for max and min, where U is for understand, draw is for draw, names is for naming variables, for is for the formula, and then max or min. So let's see how this goes. Let's look at optimal control for a crop yield of a certain plant. So here's a crop field, and the yield Y of a crop depends on the nitrogen supply which the farmer supplies to the field. And so let's call the nitrogen supply N and the yield Y, and then there's a certain formula which is based on experience, so the yield is Kn divided by 1 plus N square. And now K is a positive crop specific constant. The K will be different for different crop types. The question is, what nitrogen level is best to give the most yield? So that's an optimization problem. I wrote down the formula again. So the first step was U, so understand. So the unknown is the optimal nitrogen supply, very clearly given in the problem. What we know is the K value. Now, there's no value given. It's not said K is 2 or K is 4. It just said K is specific to the crop. But we can assume that the farmer knows what K is for a given crop. So K value is known. And then the formula for the yield is explicitly given as written above, right here. So we know Y of N as well. Draw a diagram. Well, in this case, this is not a complicated problem. We really don't need a diagram. But if you like a diagram, we can draw a little diagram. And then we supply nitrogen N2 onto the field. And so that's our little diagram. Names. So the important name is to name the optimal level which we are looking for. So let's call this N-opt. I suggested to call the function to be optimized Q. But here it's already given, it is Y. We want to optimize the yield Y, so there's actually no need to introduce another function Q. It would be confusing. So in later, harder problems, we will have to introduce a Q function, but this time we just get away with the Y. We want to optimize Y, and then the formula for Y is already given, so this is done. Perfect. So then we can move on and really min and max. So y of n. is a continuous function, and it has a domain from 0 to infinity. Now be careful. So the function itself is defined from minus to plus infinity. However, we are talking about a nitrogen level n, and the nitrogen level can't be negative, right? So that's why the domain we consider is from 0 to infinity. Now looking for maxima of y, we look at critical points, but we also evaluate the function at 0, because this is one of the boundary points which we still need to include. Maybe do that first. First we look at y at 0, because it's a boundary point. We find there's 0 yield, so this is not likely to be our maximum. So then we look for critical points, which means we have to equate the derivative y prime of n to 0. So what is a derivative? Well, that is the quotient rule. So we have low d high minus high d low. Draw a line and square below. Oh, sorry. There's a square. So it's n plus 1 square, and then the whole thing squared again. Now the numerator simplifies. This is k, and then we have kn square minus 2kn square. So this is minus kn square. 1 plus n square squared. And then this equals to k 1 minus n square divided by 1 plus n square squared. Okay. So setting this equal to 0, we get two solutions. So the numerator is 0 if n is plus or minus 1. So this implies n is minus 1 or n is plus 1. But we earlier said a negative nitrogen concentration doesn't make any sense. So the n is equal to minus 1 is discarded for biological reasons. Okay, but the other point, n is equal to 1, is relevant. And so then when we evaluate the function at 1, and so then the yield becomes k divided by 1 plus 1, so this is k half. Now we would like to know if this is max or min of neither of those. So we have two tests. We can use the first derivative test or the second derivative test. Well, the second derivative test requires a derivative of this term here. So this, I don't know. Maybe let's try the first derivative test. Seems to be easier in this case. So we look at y prime of n, and again this is the formula given above. And now we are left of 1. We are smaller than 1, then the factor 1 minus n squared is positive. So the slope is positive on the left. If we go past 1 and n is bigger than 1, then the slope is negative. So y prime changes from plus to minus. Now, do you remember what this means? So from plus to minus, so it first goes up and then goes down. So which means 1 must be a local maximum. First derivative test says n is 1 is a local maximum with value y at 1 is k over 2. So our optimal yield is k over 2, and our optimal nitrogen supply is n is equal to 1. Let's look at this fun example of the age of maturity. So the age of maturity is an age where individuals in a population begin to become reproductively active. In many populations we observe a juvenile time where children grow up, and then only if they become old enough they are able to reproduce. Now we would like to estimate the optimal age for reproduction for a Hylodrillosaurus population. And so here we have a formula for the reproductive success R, which is given as this formula. R is the third root of A, e to the minus mu A, where A is the age. And then mu is the reproductive rate of a Hylodrillosaurus population, which has been estimated from the doubling time. So the doubling time is about 60 years. So now what is the optimal age for Hylodrillosaurus to reproduce? So again we use our saying that is U draw names for max and min. So U stands for understand. So the unknown are the optimal maturation age. The knowns are a formula for the reproductive success R of A given on top. and also known as the half-life of a Hylodryllosaurus population of about 60 years. Let's draw a little sketch to see what is going on. So here we have an h-axis, A, which is the h. Okay, and then we can have young Hylodryllosauruses, or we have intermediate age Hylodryllosauruses, or we have a little bit older Hylodryllosaurus. So here we have an example of a population of Hylodryllosaurus. We have a young one, we have a medium-aged one, and we have an older one. And so what is the optimal age of reproduction for this population? Let's introduce names. So you draw names, so names is next. So the optimal age is called A opt, and everything else has already a name. We have a growth rate mu, and we have a reproductive success function R. A formula for Q, again we want to optimize the reproductive success R. This has already a name, so there's no need to introduce a Q in this example either. So now we can work on the min and max. Again, what is the domain of this function? Again, we are only looking at positive age, right? So then we have 0 to infinity, and then we can immediately compute the reproductive success at age 0, which of course is 0. So this is not likely to be a maximum. Let's look at the derivative. R prime of A is, so we have a to the 1/3, so then derivative is 1/3 a to the minus 2/3, e to the minus mu a, and then product rule, so plus a to the 1/3 times minus mu times e to the minus mu a. And then we can factor out a few things. I factor out a to the minus 2/3 times e to the minus mu a. Let's see what we keep. In the first term we keep a third, and then plus in the other term, if we factor out a to the minus 2/3, but we only have 1/3 here, this is in fact an a, and so we get minus mu a. So if you multiply this out, a to the minus 2/3 with the a here, we get a to the 1/3, which is what we should have. Alright, so I do it because now I can easily see the zeros. So we have r prime is 0 for a is 1/3 mu. So we need to find the value of mu, and we get this from the doubling time, which was given as 60 years. And we have a relation between a growth rate of a population and its doubling time, right? So we had mu is equal to log 2 divided by the doubling time t1. So this is log 2 divided by 60. Plug in the numbers and you get 0.01155. Great. Now we can take this value and sub it in here and get our optimal h. So let's do that. So then we find A opt is equal to 1/3 mu. Subbing in the numbers, I get 28.85 years. So this seems to be the optimal age of reproduction. So finally, we need to use the first derivative test to really ensure that this is an optimum. So let's write this down. First derivative test says yes, this is maximal. So now let's ask Tollo. Tollo is about 28 years old, and so let's see what he thinks about this result. So here is A opt. Yippee! I like this. Oops. By the way, I'm leaving. Bye. Let me summarize. So the method of optimization of word problems can be done by following 5 steps. The first is to understand the problem, what is unknown, what is known, then to draw a diagram, and if we do problems later which are more complicated, we actually do serious diagrams of the form which I maybe indicated earlier. We give names to all the variables, and then we find a formula for the function to be maximized. So here we had the yield, y, or we had the reproductive success, r, and then we use maxima and minima methods that we have learned in class. So I think we should not disturb Tollo. I'm sure he's now occupied otherwise.